We've determined that the magnetic field inside an ideal solenoid is uniform and that the magnetic field outside an ideal solenoid is zero. Okay, now let's apply Ampere's law once more to actually find an expression for that magnetic field, which will turn out to depend on the current cycling through our coil and also some of the dimensions of our coil. Let's let capital L be the total length of the coil, capital N the total number of turns, so 1, 2, 3, 4, 30 turns of wire here, and suppose the wire is tightly packed together so there's no spacing between the individual wires and that the diameter of a single wire is little d here. In that case, we could express the length of the coil L as the number of turns times the diameter of one turn. So L is N times D there. Okay, an Amperian loop that'll get the job done will be another rectangle utilizing the symmetry that we've got here. So let's draw some rectangular loop that encloses some of our wire here. I will number these corners 1 to 2 to 3 to 4. Let's say the length of this rectangle, this arbitrary length here, we'll call little l. And since we're enclosing current that's coming out of the page, I'm going to be traveling counterclockwise around this loop. Stating Ampere's law, integral of b dot ds around that loop equals mu naught times our current enclosed. Let's expand that expression. This closed line integral can be expressed as the sum of 4 open line integrals from 1 to 2 2 to 3, 3 to 4, and 4 back to 1. Our current enclosed here on the right-hand side will be the current running through each wire times the number of wires penetrating through this open surface bounded by our rectangular Amperian loop. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like I've enclosed 9 turns in there, so that'll be 9, the number of turns enclosed, times I, the current carried by each one of those wires. Okay, let's look again at these 4 open line integrals. As argued earlier, the B field in the ideal solenoid is only running horizontally. It has no vertical or no components in this direction. So both inside and outside, B is directed like this. Although outside, we can forget about B field because we argued last time that B is 0 outside. With that argument, we're going to say that this integral from 3 to 4, b dot ds from 3 to 4, that's 0 because B is 0 on the outside. And then from 2 to 3 and 1 to 4, B, even if it's not 0, it is at a right angle to ds. There's B, there's ds, and there's a little right angle between them there. Same thing on the 1 to 4 side. So it's our dot product that makes that term 2 to 3 and 4 to 1 go to 0. Okay, leaving us with just this first term, the open line integral from 1 to 2. Okay, so we know B is uniform on the inside, so B has the same value everywhere along that path from 1 to 2, and B is parallel to our DS's from 1 to 2, so our dot product just gives us a plus 1 from the cosine 0 degrees between them. So integral from 1 to 2 of b dot ds plus all those zeros. B is uniform along that path, so it comes out of our integral. And we just have the sum of all the ds's from 1 to 2, which will be the length of that path from 1 to 2, which will be L, little l. Little l, this length right here. Okay, so b times little l, all these zeros equals mu naught times our current enclosed. So we're concluding that the strength of the magnetic field inside our solenoid equals mu naught, and I'm going to say 9 over L times the current running through our wire. Let's generalize this a bit. Since 9 was arbitrary and L was arbitrary, I would like to define a quantity we'll call little n. This is the turn density. Turn density, little n, will be the number of turns, 9 for instance, in a given length of coil, little l. And if the coil has a uniform spacing of turns all the way through, then that could be represented as the total number of turns, capital N, divided by the total length of our wire. That can be expressed one more way. If the length of the wire is the number of turns times the diameter of the wire, then this is n over n times d. So our turn density is also equal to the reciprocal of the diameter. Of our wire. So this value is exactly what's appearing there in this equation, leading us to the expression we really want, the magnitude of the magnetic field strength, or the magnetic field strength, the magnitude of the magnetic field equals mu naught times the turn density, little n, times I. Popularly known as the Bunny equation, B-U-N-I, the Bunny equation, right there. Okay, a warning about the use of this. This only applies for an ideal solenoid. No solenoid is an ideal. No solenoid is truly ideal, so this is, of course, an approximation for the magnetic field strength inside some solenoid. And it's a quite poor approximation if your solenoid doesn't meet our ideal constraint, which is that the length L must be much, much greater than that radius R right there. So in particular, I want to warn you, by the way, this equation is commonly misused. This equation definitely does not apply if all you have is just a single loop of current, one loop like this. If you just got one loop, that is not an ideal solenoid at all. If you've got just one loop, this would not be able to give you an accurate expression for the magnetic field at the center of that one loop. We had to use the Biot-Savart law to find the magnetic field along the axis of a single loop of current. So you recall this integration, kind of brute force from Biot-Savart law to get us to this expression, which could be used to find B along the axis of a single loop, or set Z equal to 0 to find B at the center of a single loop. So this is not the Bunny equation here, and you've been warned.